Yeah, so I was talking about value adding to what Christian said. So you go out and you catch all sorts of things. We want to, sometimes they're inconspicuous. We want to be able to test what's actually in spores, what spores we might have, and whether we can fight virus and stuff like that. So I'm going to specifically talk about virus. So currently, virus diagnostics require lab testing of leaf samples. We do it serologically or by PCR. And diagnosis is made from already symptomatic plants. So a grower will say, I've got some plants that have got purpling and so forth, send them in, and we'll test them and say, oh, you've got 40% infection. Say, well, what can I do? I say, oh, not much, you'll probably lose a bit of yield and there's nothing you can do about it. So at best, it's going to be a reactive, tardy management thing, which would likely be an application of insecticide to stop aphid spreading. So this is all very reactive. So what we needed is an innovative diagnostic that allows early virus infection, which means we can plan for proactive management. So the pathogen we examined is turnip yellows virus in canola, formerly known as beet western yellows virus. It can cause over 40% yield loss when spread is high, and it's vectored by the notorious green peach aphid. And its control is obviously because the green peach aphid is reliant on insecticides, so seed dressing and a follow-up application and other agronomic things, but the insecticides are the core. And there's a diagnostic yield loss blind spot, which means that we have so when the insecticide seed dressing wears off, we have a period of time where yield losses are just as bad as if it would have got infected at a real early stage. So it's a bit of a blind spot, and furthermore, we have latency of infection, which means that plants that become infected aren't actually detectably infected until later. And this latency period gets longer and longer and longer as the plants get older. And so we also get misdiagnosis leading to wasted resources. So these sort of symptoms here, these are all virus symptoms, but they also look like nutrient symptoms. Same sort of response to any stress for canola. And obviously, if you go and then apply some N or something to that, you're essentially wasting because it's actually infected with virus. So the technology we explored is the Genie 2 lamp machine, which I've got it there if you want to play with it later. It essentially amplifies RNA and DNA so we can find any biological specimen. Detection can be achieved in 45 minutes. I've got it in a suitcase there, so you can literally take it out in the car, take it out in the field, and it's really easy to use. Anyone can use it, it's easy. So what we did was we got a whole bunch of aphids. We chucked one aphid that had virus in it in 100, crushed it up with this little screwdriver thing, put it on the lamp machine, and we're actually able to detect all the way up to 1 in 100 aphids. And this is amplification of RNA. So it's very sensitive, and what this means is that when we catch a whole heap of aphids in the field on yellow sticky traps and so forth, or glycol traps like Christian said, we can actually detect virus within the aphids. So we know that the virus is coming in before it's actually established in the crop. The other thing we developed was primers, which allow us to do the assay for green peach aphid itself, so we can detect green peach aphid DNA. So we wanted to field validate this. It's one thing doing it in a lab, but another thing actually showing it to work in the field and what it actually means. Does it give you a useful indicator of risk? So we set up surveillance sites around from the line from sort of Mount Barker through to Esperance, and then I did a few out in Northern, Tujo, and we're monitoring aphid numbers on sticky traps, pulling off the aphids, testing by the lamp machine, and then relating this to turnip yellows virus spread in the crop. So we got a couple of interesting results. This is just a little bit of a snapshot. So we have one case here where we had a high amount of spread, and we detected both green peach aphid DNA and turnip yellows virus RNA early. On the flip side, over in Gibson, we got a very minimal spread, would have led to absolutely no yield loss, and we didn't find green peach aphid or turnip yellows virus until after sowing, and in the case of turnip yellows virus, not until July. So you can see there that there's a sort of relationship between the time that we actually find these targets and virus risk. So the future research for and potential applications of this technology. So we're gonna do barley yellow dwarf virus in cereals this year. Other inconspicuous pathogens, I said fungal spores before, and we want to use it in these smart trapping programs and surveillance programs So we need to get more of this infrastructure out there, the sort that Christian was talking about, and then value add to that by using stuff like this. And we want to hybridise so detection time and all that with forecasting systems that already exist that aren't being used. For instance, with that virus I said there, we've already got models that actually are quite good at predicting spread from climatic data. So if we combine real-time data with climatic data, we can actually get a useful, and as long as we can get that on a useful format for growers to understand, we can get really accurate and spatial sort of risk maps. That's what I'm looking for. So, and also the other thing we can look for with these, because pesticide resistance essentially is just a change in the genome, so we can actually be able to detect that. CCDM are already doing that with fungicide resistance, and we can also use it for on-site detection of biosecurity threats like the old Russian wheat aphid, which got brought up today. I won't talk about that. Cheers. Thank you.